In this video, we shall discuss a problem that illustrates how fast ice melts on a frozen lake. So here is the problem. If the solar radiation energy from the sun incident per second on the frozen surface of a lake is 650 watts per meter squared, and 68% of this energy is absorbed by this ice, how much time will it take to melt 1.5 centimeters thick layer of ice? The ice and water beneath it are at 0 degrees Celsius. The first thing to note is this 650 watts per meter squared number is the intensity. So the intensity of this radiation from the sun is 650 watts per meter squared. Another thing to note is this is a process of melting of ice into water. So the type of heat that we are interested in here is the heat of fusion, which is given by the mass of the ice that melts times the latent heat of fusion, L sub F, and this is a constant temperature process. So let's calculate the rate of energy per second. Heat energy, that is, from the sun that is being absorbed by that ice. And that is simply d over dt times mLF from this equation. LF is a constant, so you can take that out of that derivative. So it becomes LF times dm dt, where m is the mass of the ice that melts. Now we know mass equals density times volume. So the mass of ice equals the density of ice times the volume of ice that melts. So let's substitute that information in here, and we're going to get density of ice times the volume of ice that melts. The rate of change of that times L sub F equals the rate of thermal energy that is being absorbed. From a standard tables, we know the density of ice is 920 kg per cubic meter. Now let's look at this volume of ice that melts. That is the volume of that ice layer on the top of that lake. So let's model it in following way. So it's almost like a cuboid with a surface area A. This is where the sun shines, and that is the thickness H. So the volume of ice equals the surface area times that thickness of that ice layer. Let's substitute this information in here, and it becomes A times H in that bracket. Density of ice is a constant. The surface area can be taken to be constant. What changes is the thickness of that ice layer. So we can write this term in a following manner. L sub F, take the density of ice out of that derivative sign and also the surface area of the derivative sign, leaving only H in it, dH dt. We can look at that derivative dH dt as the thickness of that ice layer, delta H, over the time interval delta T that is required to melt that much ice. So let's substitute that information in here. Delta H over delta T. So this L sub F is the latent heat of fusion for water, and its value is 334,000 joules per kg. One other thing is this intensity heat tells us every second 650 joules of energy falls on a surface area with a size of 1 meter squared. Of that, only 68% is being absorbed by this layer of ice in order to melt. So that means 0.68 times 600 650, which is 442 joules of energy that falls every second on an area with size 1 meter squared. And this is the amount of energy that is responsible to melt that much thickness of ice. So let's come back to this equation. How do you turn watts into watts per meter squared so that this information can be used? All you have to do is to take dq dt and you divide that by A. So when you do that, dq dt over A is quite simply all that. And this is the same as 442. So now let's substitute all the information that we have. L sub F is that number, so 334,000. The density of ice is 920 times delta H. Delta H is the thickness of that ice layer that melts, is 1.5 centimeters. So 1.5 divided by 100 to convert that into meter, over delta T, which is what we want to find. Remember, we want to determine how much time it takes to melt that thick of a layer of ice, and all that equals 442. And from this equation, you can determine delta T. And if you do the calculation, delta T turns out to be about 10,428 seconds, or in minutes, about 174 minutes, or in hours, it's about 2.9 hours. So it takes about 2.9 hours for the sun with radiation intensity of 650 watts per meter squared to melt 1.5 cm thick layer of ice on the frozen surface of that lake. This solves the problem. Thank you for watching.